Ever wonder how your brain's electrical signals could control a computer? It's not science fiction. It's the cutting-edge world of brain-computer interfaces, BCIs. Today, we're diving into a breakthrough study that's making these systems smarter, faster, and more adaptable. Let's break down how researchers are decoding the brain's language and why it could change lives. At the heart of this research is a challenge. BCIs need to interpret motor imagery, the brain's signals when you mentally picture moving your hand or leg. But here's the catch. Every brain is unique. A system trained on one person's data might fail for another. That's where MIRepNet comes in. Think of it as a universal translator for brainwaves, designed to work across different people and setups. How does it work? MIRepNet uses a clever two-step approach. First, it learns general patterns from a wide range of brain signals, like studying a library of languages to understand grammar. Then, it fine-tunes itself for specific tasks, like recognizing when you're imagining moving your right hand. This hybrid strategy lets it adapt quickly, even if the data is a little messy or incomplete. Here's where it gets really cool. The model doesn't just rely on raw data. It uses a technique called masked reconstruction, kind of like teaching a kid to solve a puzzle by showing them only part of the picture. By hiding some brainwave data during training, the model learns to guess the missing pieces. The result? A system that's not just accurate, but resilient, like a detective who solves a case even with a few missing clues. The numbers back this up. On a key dataset, MIRepNet hit 81.77% accuracy, way ahead of traditional methods like CSP plus LDA or deep learning models like EGNet. But the real surprise? Even when researchers hid half the data during training a 50% mask ratio, the model still performed strong. It's like a chef who can whip up a meal with just a few ingredients, versatile and reliable. So why does this matter? Imagine a paralyzed patient controlling a robotic arm with their thoughts, or someone with ALS communicating through a computer. The more accurate and adaptable the BCI, the smoother the experience. MIRepNet's ability to handle diverse brain patterns and incomplete data means these technologies could become more accessible, reducing the need for tedious calibration sessions. But here's the bigger picture. This isn't just about better accuracy. It's about building systems that learn like humans. By combining pre-training, self-supervised learning, and smart data handling, researchers are creating BCIs that don't just process signals, they understand context. It's the difference between a robot following a script and a person adapting to a new situation. Next time you hear about AI and the brain, remember, it's not just about speed or power. It's about how well the system listens and adapts. Thanks for watching and stay curious. The future of BCIs is closer than you think.